Okay. Let me confirm once more whether you can hear me, Aladi. Hello, can you hear me? Hello.
Yeah,
Yes,
it's okay. It's okay,
Okay.
Kasim.
Okay. Thank you so much. Welcome again to the second session. We had a session yesterday on on a general topic, which was how to conduct research from start to finish. Today's topic is going to be more specific for lovers, especially of machine learning and structural dynamics. So Enladi is going to talk to us about. He's mainly going to introduce us to machine learning for structural machine learning for structural health monitoring. So he recently published a paper on a similar topic. Aladi is a final year master student. He's going to graduate this year, and I hope that everyone will enjoy spending this valuable time with him as he takes us through this very, very important topic that is very hot in the world now. That is application of artificial intelligence and artificial intelligence methods to solving a wide range of issues, including structural health monitoring and related issues. Thank you so much, Ladi, for agreeing to honor us and sharing some insights with us. Thank you very much. Yeah, you can go ahead and share your screen. Hello, we can't hear
all
you.
right.
Okay,
All right, thank you
we
very
can hear you now. We can hear you now.
Thank you very much, sir. I'm grateful. Thank you for the opportunity, and I welcome each and everyone that is here. As he already mentioned, we'll be talking about structural health monitoring and particularly using machine learning algorithm for the to perform structural health monitoring. I'm deeply honored, sir, for the opportunity. I believe I'm not the only person. I'm not the best person in this. So we'll try, and even as we share and learn from each other. Thank you. So as I have already mentioned, I believe my screen can be seen.
Yes, we can see your screen.
All right, thank you very much. So as I mentioned earlier, we'll be dealing with structural health monitoring and particularly using machine learning. So because of that, we'll briefly introduce the structural health monitoring before talking about the machine learning. And then we go ahead and see an overview of the work I recently did. Now, talking about structures and structural health monitoring, we all know that the level of technology has reached a certain level where we construct mega projects
Sorry,
despite the fact that
sorry for interrupting. Can you play your slide? Can you play it so that it's full? It's down bottom. No, bottom. Okay, that's okay. Also.
Can you see it now?
Yes. Thank you.
All right, thank you. So as I was saying, we've reached a certain level of technology now where the construction of mega projects is to some extent not limited by the level of technology, in the sense that we can build as much as we want, we can build as tall as we want. Of course, there are still some limitations, but then we have achieved tremendous success in that aspect. As we can see here, we have some very famous structures, and we can see there are some of basic information about them. So talking about the information, you can see there is cost, there is number of floors, and there is number of people that it can occupy. And that some extent points the risks that is involved if in case there is any kind of failure. And because of that, we all know that we normally perform some structural analysis before going into the construction. So there is always a design process before even starting the construction. And we mostly use our softwares to do that analysis. Now, even after doing that, and even at this design stage and during the construction and after the construction, there are still some kind of uncertainties that we often deal with. So, and because of that, there are some cases that we still encounter, some risks, some failure that we encounter, as you can see in the pictures here in this slide. We have some failure. There is one that happened in 2013. That is in Bangladesh. About 1,132 people died, 2,500 injured, and the main cause is negligence. And there is another one in South Korea that happened in 1995, which 500 people died, and the cause is poor decision, change of purpose, and the rest of them. And we can see many of them even in this list. And of course, we have even a lot of them that I didn't even mention. So because of that, we always don't want to take any chance. So we always try to minimize such kind of risks as much as possible. Now, what are the causes of all this? The causes, as I mentioned earlier, that there are uncertainties right from the design stage to the construction stage and even in the operation. Now, in the design stage, we have some assumptions that we made that may not necessarily be realistic. For example, we have assumptions in the material properties. We have assumption in the site properties, for example, the geological condition, and even, for example, the load and the rest of them. So all those things are things that we assume. Like, of course, we try to calculate them as much as possible, but then it's difficult to get the exact quantity or this exact the real life scenario is difficult to capture that. So because of that, we normally follow that design with a monitoring process. And even in the operation stage, we also have some cases where the intended purpose may be changed. So in that case, you have to like go back to your model and still kind of make some adjustments, even while the structure is on ground. So how do we handle these scenarios? I have some question here. So we handle them by monitor. How do we monitor? We measure. And how do we measure? We use sensors to sense, that is to acquire data. And then how do we interpret that data? We process, analyze, and make comment, that is conclusion, and make forecast using statistical and data science tools and models and algorithms. Now, these tools and models are what we presently in the present days refers to as data science, or where we have the machine learning algorithm, we have the neural networks, and the rest of them. So that is how the data science that we are dealing with is interconnected to the structural health monitoring that we are talking about. As I mentioned, we use sensors to measure data from existing structures. That structure can be a building, can be whatever. So we use sensors to measure that data, and we use data science tools and statistical tools to analyze that data and make predictions, which one of them is the machine learning that we're going to talk about. Now, talking about machine learning, what exactly is that machine learning? I know of course, most of us have idea of what a machine learning is. And I believe with this picture here, we will even understand it better, because sometimes it's confusing. Like when you talk about artificial intelligence, you talk about machine learning, you talk about deep learning, you talk about data and the rest of them, all those things can be confusing. So from the picture, as we can see, machine learning is a subset of artificial intelligence, while deep learning is also a subset, that is, a subset of machine learning. So I believe with that, we are able to get a clear picture of that, of the whole concept. Now, machine learning can be defined as a technique that enables systems to learn and improve based on past experience without the need for explicit programming. Of course, when we talk about explicit programming, that is when it comes to the deep learning, because you have to define every parameter. You have to give it you have to give it a program. You have to design a program for it, and then ask it to perform whatever tasks you want it to perform. While a machine learning is kind of a simplified program where maybe someone has already built it. So your own is just to make some 1 or 2 changes, and it will fit into your data, and it will be able to perform the tasks that you want it to perform. Now, what are these types? Some of the types of this machine learning include it's basically divided into 2. That is the supervised and the unsupervised. Now, for the unsupervised, we usually use it for clustering, which is an example where we have the KNN. And then, but the most common one is the supervised learning. And for the supervised learning, we have basically 2 categories. There is the classification and the regression. Classification can be binary or multi-class. That is where you group your data into different classes. And regression is where you have like a series of data that you have to predict, that you want to predict like maybe a certain value from the data. Now, the main difference between the supervised and the unsupervised is the fact that for the supervised, regardless of whether it is classification or regression, the supervised you always provide an input and output data for the model you are training. For the model you're training, then it tells us, okay, this is the output data, this is the target, and this is the input. Now, if I put this, I want to get this. Now you split your data, of course, into 2. Then you have the testing and the training. Now for the training part, you also have the input and the output. Also for the testing part, you have the input and the output. However, during the testing process, because already you've trained the model during the training process, now in the testing process, you don't provide it with an output. You only provide it with an input. Now, based on the training you've trained your model, it will be able to make prediction from the input data you have provided during the testing process. Now, the result you've gotten from the testing already, because you already have your output, that is in the data set, in the test data set, you already have your model, your output. So you provide it with the input. Now, whatever output you get, you compare it with your own output. That is the output from the model and the output that you originally have. So that is how you perform the test and the training and the testing. Now, that is the basic difference between the supervised and the unsupervised. The unsupervised, you don't provide it with input or output. You only provide it with input data. Now the machine will be, the model will be able to perform the prediction on its own. While for the supervised learning, you provide it with both input and output. And also both the input and the output, you also have a testing data set and you have the training data set. Now for each in machine learning in general, you have a procedure you carry for carrying it out. That is, for the procedure we have, first of all, you acquire your data and prepare it. Now, preparation is like pre-processing. Sorry if I'm too fast, please let me know. Hello.
Oh, your pace is okay.
All right, thank you. Now, as I was saying, for the machine learning, you have a procedure. The procedure is, number 1, you acquire and prepare your data. How? Of course, there are different ways you can get your data because there are different types of data. Now, depending on what kind of data you're using, sometimes it can be a model. You prepare your model, so you will simulate the scenario, whatever scenario it is that you're modeling. You model it and you get your data, whatever data you need. Then that very data is what you use for the training. Now, in the training, before the training, you process data. Some people, like in some cases, you will download the data. So if you download the data, there is possibility that there are some missing values or there are some errors. So you have to do what we call explanatory data analysis, which is part of which is pre-processing. Now, in the explanatory data analysis, you visualize the data and check for missing values, you check for errors. For example, sometimes there are what we call outliers. There are values that are not reasonable in the data because you already know what you're doing. So you know the kind of data you're expecting. Now, going through the data will enable you to see, okay, are these values, all these values, are they reasonable or not? Now, if they're not, whatever you see that is not reasonable, you then eliminate it. That is, you remove the outliers. That is what we call data cleansing. And whatever, for example, because your data is always arranged in rows and columns. So whichever row you notice that there is a particular cell or there is a column that is missing, you remove it. That is also part of the data cleansing. So all these are part of your data preparation. You make sure you have an accurate data. After you've pre-processed it, because the accuracy of your model would depend on the accuracy of your data. So that's why this stage is very important. Regardless of the source of your data, you have to make sure that, okay, this data you're feeding into the system is an accurate data and well processed and cleaned data, because of course we all know that computer works based on garbage in, garbage out. So you don't want to give it a wrong data, which will ultimately result in getting a wrong model. So that's why this stage is very important. Now, the second stage is to choose and train the model. This is also an important stage. Why? Because you may have a very good data, you may have a clean, well-processed data, accurate data, but then choosing a wrong model, there is a model that doesn't fit into your data. And especially if you're talking about the machine learning, remember I said it's something that has already kind of programmed. So you just adjust one or two things to make it like perform very well on your data. So now, when you select the wrong model, it will result in also poor performance on the data set. So you may think maybe something is wrong with your data. No, it's the model that you select. I will, if time permits, we'll go through the process and see how we go about that. And also, after choosing the model, the next stage is to train it. Now, the training is because by default, machine learning algorithms have what we call parameters, like hyperparameter tunings. For those of us that have like a basic understanding of it, there is what we call hyperparameters tuning. Now, hyperparameters is where you make some adjustments so that the model will perform very well on your data. So you choose your model, you train it based on the data that you have. Now, the training is where I said we have input data and output data. Now, in the training stage, you provide it with both the two data. And of course, in the machine learning, for machine learning training, the larger the amount of data, the higher the probability of having a good model, that is the performance of the higher the chance of your model to perform very well. Now, after that stage, the next stage is to use the test data to check the performance of the model. That is what we call model evaluation. Okay, you've trained your model in the previous stage. Now, how do you know that your model has learned very well? How do you evaluate the performance of your model? Is by using a test data. Okay, let me say this again. After getting your data and processing your data, cleansing and everything, like arranging it very well, the next thing is to split your data into two. That is the test and the train and the test. Now, each of these data set will have the input and the output. Of course, you can also do it the other way around, in the sense that you can split it into input and output, then split it again into test and training, whichever way is convenient for you. But then just know that you have a training data set and you have a testing data set, and you also have an input and you also have an output. Now, the testing data set is what you use to evaluate the performance of your model. Now, after evaluating the performance, there is also what's it called? There is a prediction. Now, after you perform the prediction, there are metrics used to evaluate. Of course, for regression, most of the metrics are what we are familiar with. You have the mean square error, mean absolute error, and also coefficient of regression, which is the R squared. So those are some of the metrics. Of course, there are other metrics as well, depending on what you're doing. For example, classification, if it is a classification task, it has its own metrics, which are the specificity, precision, F1 score, and the rest of them. So depending on the task you are performing and depending on what you want, for example, in engineering, we always consider economy and safety. So you don't want a model that will, for example, estimate, overestimate, or underestimate too much. So that's why you always have to optimize these two key factors, which is the economy and the safety. So that is that. In fact, most of them have even a provision for you to select which of the metric do you want to prioritize. Now, there's a relationship between like the target, your target, and your priority, because the prediction is made based on what you want to achieve. I don't know if that is clear. Yeah, so I think that is that basically about the procedure. Now for the overview, of the previous work. Now, I did a research on settlement, bridge peer settlement, but then what I use, the data set, my data set is not from the bridge itself, but from a train, because when there's a settlement on bridge, there is a change in acceleration of a train running on that bridge. Now, the changes in the acceleration of the train is more like amplified than when we consider the changes in the acceleration of the bridge itself, because of course the train has the train's dynamics has some flexibility relative to the bridge itself, that is the bridge deck and all those bridge structural components. So that's why we choose the train acceleration response. Of course, we will have like more significant values than when we are considering the bridge. So that is what I did basically. We consider a CRS 380A train model, and we use now the bridge numerical values of the bridge deformation. For example, just as we can see in the picture here, when there's a deformation in bridge, there's at point B, and there's a track on the bridge, the profile of the rail will have some deformation as well, like depending on the magnitude of the settlement. Now, that is computed using this formula that we can see here. Now, from the formula, we're able to establish the rail profile. Now, this is what we can see here in this plot here. I don't know if you can see my cursor, my mouse pointer, I mean.
Yes, we can see.
All right. So this is what we obtain from this formula.
If you hold on control, it will turn red. People can see better.
Okay.
All
right. Thank you. All right. So this is what we're able to compute using this formula. Now we compute this as the rail profile. Of course, this is because we don't just assume the bridge, the train is just like start running on the bridge or automatically. It must have covered some length, some distance before reaching the bridge section. So that is a more realistic assumption. So that's why you can see here is flat, and then we have the settlement case here. Now this portion that we're seeing here is more like this portion here. That is from point A to point C. That is where you start from here, point A, point B. That is the maximum deformation point, and then point C. Now we have 5mm settlement, we have 10mm settlement, we have 15mm settlement. Of course, we didn't just consider the 5, 10, and 15. We consider 15mm settlement at 1mm. It's just for the sake of clarity that we just select the 5, 10, and 15 so that it won't be too congested. So we consider 15 millimeter at 1 millimeter interval. So in that case, we're able to get 15 different real profile using this same formula. Now, we know that in reality, the track profile will not be as smooth as this. Why? Because we have some random irregularity due to some factors, maybe geological or site condition and the rest of them. So we always consider a random irregularity. And how do we match these two? We compute this random irregularity. Of course, there are some codes that guide the computation of this. And also, we sum them together with this. There is each of these settlement will have a corresponding random irregularity that will sum them together and put them as in excitation into the as excitation input into the train, so that the train will have some kind of acceleration. Now there is 15 here and we have 7 here, 7 random irregularities. So if you do the maths, you will have about 100 and something, if I'm not mistaken. Now, I mentioned earlier that we need as much data as possible in order to have a more realistic machine learning model. So that's why we consider 7 and 15 here. And of course, the 15 is limited because when we have a severe deformation, of course the train will not be allowed to run over the bridge. So it's reasonable to limit it to just 15 millimeters. So that's why we just consider 15 here, and we consider 7 here to be reasonable as well. So that's how we got our real profile, and this is what we use as input. Of course, these are the values that we gotten from this plot, from this computation. Sorry. Yeah, these are the values. This is for the deformation and this is for the random irregularity. So we combine we sum each of these with each of these. That is, for example, 1 millimeter settlement with irregularity 1, irregularity 2, irregularity 3, irregularity 4. So that's why I said you do the math, it's a kind of something like permutation and combination. So you combine them together and you're able to get different kind of scenarios. And of course, for the speed also, it's another factor. So consider like 4 different speeds. That is from 250 to 350. Now, how do I do this? I use for loop for the summation. That is for merging the two kind of deformation. That is the random irregularity and the settlement deformation. Because if I say I will do it with hand, it's like something that will be tedious, because if you take it, it's the number of rows is about 200 and something here, and the number of rows here is about 500. So it's something that requires the fastest possible way. So I just use for loop in my Python. And of course, this is the code that helped me to do that. There is this code that you can, for example, if you use a data frame on the Python, notebook, you can save the file automatically in your system as a CSV file, comma separated value. So that is what I use to combine the two. This is for the irregular. This is where I load my data, that is into the notebook. Then this is like the column title, and this is the for loop program that I use. I don't know. I believe that is clear. Of course, because of the time, we have to kind of rush. We'll try to go through as much as possible. Now, after that, the next thing I will do is, after merging them together, is to get a TRE file. TRE is track random excitation. Now, track random excitation is what I use as an input file to simulate the settlement. That is to tell the software that this is a track, and the track is on a bridge, and the bridge has deformed. Now, whatever profile, whatever form that these numerical values. Of course, we're all familiar with all those graphs and plots. So there is this plot I've shown us earlier on. So the combined one together will give me the profile of the track, and that is what the train will run over. And based on that, I'll be able to get to capture the acceleration response of the train at different time, that is at different positions. And that is what I'm having here on the left. That is a plot. Now the plot, I just for the sake of clarity, I just select some of them and plot them here. This is for 15mm settlement, and I consider 4 different speeds, as I said earlier on. So you can see that there is a peak. There are some peak points, and that is just what I consider for my input data, as that is in the machine learning algorithm. Now there is how do I extract these points from here is another thing, because I don't just take all this into the machine learning model. It doesn't make sense. So I just have to extract this minimum, maximum, and of course their time, because if I didn't consider the time, that is when it occurs, it will be as though it's the same thing for all the 4 different speeds, and that may not be reasonable, because of course the train has to run at different speeds. So whatever where speed the train is running on, and whatever settlement magnitude it is, the bridge has deformed, then we have to consider that as a factor as well. Then we also consider the influence of the irregularity. We can see on this in this plot. So that is that basically. Now the next thing is for me to extract this peak points, as I said earlier on. I extract this point. How do I also do that? I also use some code to play around that, and I was able to extract my values. Now this is like the raw data. I said we have, for example, acceleration is like a function of time, right? So at different time, you have different acceleration. So this is like a good example of the raw data that I had, because we have different irregularity. We have irregularity number, for example, irregularity number 3, irregularity number 5, and the rest of them. All of them have different values, and we have different values for different settlements. So that's why I have this kind of huge data, and I have to play around and extract just the key important features that I will use for my machine learning. Now, I also use the same for loop to be able to play around this. Of course, before the for loop, there are some other codes. Now, as I said, for example, there is 300. This is where I load my data. If you can see, this is where I load my data. I have 350 km/h acceleration result. That is, I have 325. Oh yes, this is for my main thesis. But for the paper, I just use 4. But in the thesis, I use like 7, I think. Yeah. So it's the same procedure. So I just load my data here and then play around with it and do some some coding, and I was able to get some just the features that I want in this table here on the right, where I'm pointing my DC, my cursor, my mouse. Now for the input data set, as you can see, I have just the maximum acceleration and the minimum acceleration. I have maximum acceleration time and minimum acceleration time. I also have the speed as a factor. This is for the 200. Of course, there are, you can see the dot, dot, dot. There are other speeds also. Now I have the irregularity. I also consider the irregularity, and I have settlement as well. Of course, if you remember, computer doesn't understand this language, so it has to be converted to a computer understandable language, which we use the coding, I think, mapping, binary mapping or something like that, futures mapping. So that is that basically. So this is like my input data, and I save it also. I save it as, like, I export it as CSV file, then use it as the input file for the input data for the, what's it called, for the machine learning model. Now, this is the data I earlier saved. If you remember, I said I saved the data here, like using this code. I export it in the form of CSV. Now, after opening it, this is what I have. This is like my data now. This is my data set. It's ready to be used for the training of the machine learning model. Now, how do I use it? For example, what is the next stage? The next stage is for me to select my model selection, if you remember in the procedure that I explained earlier. So the next thing is for me to select model. How do I select model? In this case, there is this package called PyCaret for us who are beginners. Of course, you don't have to go and start cracking your brain and like trying to find out which one is which and which one is best for my data set. So PyCaret helps you to select a model, a machine learning model based on your data. You just, what's it called? You just install the package, then load the data, and then play around, you'll be able to get your result. And now the PyCaret has lots of machine learning algorithms, and based on the data that you provided, it will train those machine learning algorithms, and it will like rank them in the order of their performance on the data. So that is what I did. And from the figure here, if you can see here, this is the result I obtained from the PyCaret. Now it lists different machine learning algorithms and give me their performance in the order of their performance. Now the best based on the PyCaret, the best is extra-tree regressor. Extra-tree regressor, which is its R squared is 0.96. That is about 96% accuracy. And the other metrics as well, which is the mean absolute error, mean square error, and root mean square error. Now, I was talking about the metrics before, that it depends on the metrics that you prioritize. Now, based on the metrics that you prioritize, that is how the PyCaret will rank these algorithms. Now, what I did was I just select three of them. I picked 3 of them and train them, because I have to tune them, because this one, they just use the default parameters that are in the PyCaret. So you can select whatever you feel is best for you, then go with it. Now I select just 3 from these ones, and the ones I selected were extra-tree, gradient boost, regressor, and random forest. Now you can see in the PyCaret, it says extra-tree is the best. While in my final result, I realized that the gradient boost is the best. Now it depends on the data set. In fact, sometimes maybe if it is a different data set, this this may not be the case. Maybe like some other kind of algorithms will be the best. So it just depends on the data set that you use. And just before I proceed, one major limitation that I noticed as at then, I don't know whether they have upgraded, is the fact that it doesn't work with any version like higher than Python 3.8. So then I had to uninstall and reinstall again. Like the highest version it is compatible with, there's the PyCaret, is 3.8, Python 3.8. Anything above that, it doesn't work. It will just show you error. So that is that. Now, I thought we wouldn't be able to finish this early. All right. Now, we can, I don't know if there is any question. Otherwise, we can go and check the this thing, what's it called? The models that we have.
Yes, I want to ask a question.
Okay, sir.
Uh, Sorry, Wendell, for the good presentation. My first question is on the unsupervised and supervised approach for checking, for modeling machine learning aspect. Please, what situation do you use any of these, and what are their strengths and weaknesses?
Okay, for the supervised and unsupervised. Now in the unsupervised, for example, you have a data set that let's take, for example, you have a data of staffs in an organization or a company. Now the data set comprised of males and females, for example. Now we know in the data set there is what we call features. For example, let's say height, age, weight, and the rest of them. Now, if you have that data set and you want to, okay, you don't know who among it is not labeled as males and females. For example, you don't have any feature for gender in that data set. Remember, I'm giving an example of an organization that has staffs. Now you have their information, but the data is confused, like is silent about their gender. Now, based on their age, their weight, their height, maybe any other feature, if you input that data set to an unsupervised machine learning algorithm, it will be able to tell you, okay, it will be able to group the data into two.
Okay.
I don't know if you understand that. It will be able to group the data into two. So that is the case where we apply supervised and unsupervised. It can also be applicable to, for example, maybe in biology, for example, flower. You want to group flowers into two, like their information. So unsupervised can work. And when it comes to supervised learning, you have all the information you need, but the information you have is just for the past maybe years or days or weeks. But you want to, however, you want to use it to predict what will happen in the future. So now, for example, depending on what you're predicting, let's say it's a sale, like for a supermarket, you have maybe the number of customers, you have a location, you have their salary range, and the rest of them. Now you have on this, let's say on Monday, you have this sale, on Tuesday, you have that sale, on Wednesday, for example. Now, that is the data you have on ground, but you don't know, you want to predict maybe in the next, let's say 5 days, what will happen, what will be your sale, how much will you earn? Now you can use that data. Okay, already you have it. You have your customers' information, and you have the amount of the money you earn, like previously. You want to predict in the what will happen, how much will you earn in the future. That is when you use the supervised learning.
Okay. Okay.
Yes. Also, for the supervised learning, we have classification and regression. Regression is, for example, just the example I gave, like the amount of earning. However, for classification, we can use the example we gave in the unsupervised, that is for gender. Now, in the case where you have the future for gender, you have male and female. Now, for example, you want to predict, okay, how many male employees are we going to have in the future, maybe in the next 10 years? You can use the supervised learning classification algorithm.
Okay.
Yes, sir.
Thank you. Please, how do you generate irregularity in cases of monitoring issues that has to do with environmental, in terms of what you discussed before on the issue of maybe site specific issues that has to do with a particular site? Because I don't know, I saw a group of data that you generated on issue of irregularity. I don't know how do we do such a analysis? How do we come up with such a random generation?
Yes, for this we have formula, and like based on empirical There are empirical formulas that are based on statistical experiment. For example, on the track geometry, you have for different kind of tracks. That is whether it's for high speed or normal speed or heavy freight or passenger and the rest of them. So there are codes, there are coefficients and formulas and all those what's it called, provision. They are on ground that you can just follow and get your data that you want. But in the case of like other kind of scenarios, mostly the data set has its own kind of randomness. Like, for example, it's unrealistic if I use just this smooth, what's it called? It's unrealistic if I use just this smooth curve as real profile. It won't be accepted because it can't just be this smooth in real sense. So I have to kind of merge it with this random irregularity, which in other cases, they may call it noise. So most data, for example, like in the case of shopping a supermarket, the data itself, when you plot it, you see that there are some kind of randomness. So that one, in that case, you don't have to even go you don't need this. You don't need the random this thing because the data on its own is already random. So to some extent.
Okay. Thank you.
Sir. Please, are there other questions, or we can go ahead and check maybe the model, how we do the training and the testing? All right. Now, for the training and the testing, let me just share the screen again. I don't know if we can see it, right?
Yes, yes.
All right, thank you. Now, the first thing you do when performing a machine learning task or a prediction task using a machine learning, not just machine learning, even in neural networks and all those kind of programming, the first thing you do, you import your packages that you will need for that. Of course, you can also do it like subsequently, depending on when, but the rule of thumb is that you import it like just at the start. Now, after that, you load your data. For example, now I use pandas.read-csv. I believe this is something we are all familiar with. You provide the location of the data set. I'm using PD because when loading, I shorten it. I believe that is something easy to understand. I believe we all understand that. So the next thing is I import it as raw data. Now, my raw data is this. This is the data set I've already obtained from the result, and the result I processed, that is from the SIMPAC. And now there was a settlement level I assigned to it. Settlement level in the sense that I tried to group the settlement. Maybe like, for example, from 1 to 5 as group 1, 5 to 10 as group 2, and 10 to 15 as group 3. So in this case, I don't need it. So I just drop that aside. That's why I use this dot drop. Now I visualize my data. I just tell the Python that I want to see this data as data. This is what I have. We've already seen this. This is maximum acceleration. This is minimum acceleration. This is maximum acceleration time, minimum acceleration time, and I have my speed here. My speed, I said it ranges from 350 to 200, and I have the irregularity and the settlement value. Now, I may not need this irregularity as well, depending on what the correlation shows. Now, the next thing is, what I did was I standardized the speed. For example, it's a common practice for you to, when you have a data set where the range of values differed significantly, it's good that you standardize it in the sense that the range of the values should be from 0 to 1. So I standardize my speed, because if you look at the data very well, you see the maximum acceleration is from 0, is less than 1. The minimum acceleration is less than 1. The maximum acceleration time is around between the range of 1, or let me say 0 to 3, if you check it. Then, but for the speed, you see we have like 350 some kilometer per hour. So if I didn't standardize it, there is a tendency that the model will prioritize the speed over all the other features. It will assume that, okay, speed is the most important feature. So standardizing it will mean that, okay, the model should treat each of these equally. Now, that's where I standardize my speed. Now, after standardizing my speed, you can see now the speed value range is from 0 to 1. So that is just what I mean by the standardization. This is part of what we call the data pre-processing. Now, I do the future correlation check, but before the future correlation check, remember I was saying you should check the data and clean any kind of missing value or outliers. Now, although my data is a model data, so I am sure of what I have, but in the case where you download the data, you need to do this. So this may not be necessary in my own case, but I still did it. So I check whether there is any missing value. But of course, from the figure here, you can see that there is not any missing value. Now, the next thing is to check the correlation. Now, correlation tells you which feature is important and which one is not. Of course, in my own case, I just have, I have few features, like a few columns. I have few columns, but in other, there may be situations where you have like maybe like 20, 25, or even 50 columns. In that case, you need to like try to narrow down just the most important features, just the most important. That is where you do the feature correlation. Now, feature correlation tells you which one is related to your output, your target most. For example, I have the features settlement, maximum acceleration speed, maximum acceleration time, maximum minimum acceleration time. Now, you see, for example, settlement and settlement, of course, will be one. Their relation, settlement and settlement. The vertical, I'm talking about the vertical and the horizontal axis. This is settlement. This is the same feature you're seeing here, is the same thing here. Now, how you check their correlation is this values tells you their correlation. So if I'm to check, for example, maximum acceleration and the settlement speed, you see their correlation is 0.88. That signifies a strong correlation. So you do this, and in the case where you have like a lot of features, this is what helps you to know which one to eliminate and which one to keep. But in my own case, because there are few, I just keep all of them. The next thing is to split my data into input and output. Remember, I mentioned input data and output data. That is in the case of supervised learning. So that automatically tells you that this is a supervised learning, as supervised machine learning. Now I split it into input and output. For the input, that is, I said X, I assign X to be input and I said Y to be input, output. Now from this, I said X is equal to process-data.alog, and for all the rows, and from the first column to the second to the last column, that is what this -1 means. So this is what I assign. That is to say, from this row here, from this column here to this one, from this column here to this column here, they are all part of my input data, while my output data is just the settlement. Of course, that is my target. That's what I want to predict. And I'm using all of these to predict this. So that's just what I did in the input and output as data split. The next thing is to split my data into test and training. Now, test and training, in most cases, what we use 20% for testing and the remaining 80% for training. So for that, remember I said you need to import all the packages that you will need, but that may not always be necessary. So I imported my sklearn.model selection. Then I use the test split function, and that is what I use for this. And for this random state, I use 20 here that is to fix it. It's constant because the process is set of data again. So I just fix it so that whenever I run it, it will give me the same set of data, not like not be changing anytime I run it. So because I know there is tendency of error, so I don't have to do and do and do again and be getting different values. So that's why I use the random state. Remember, I said most of them have their default parameters. So I didn't put 20 here. This one, either 21, whatever value you put, just make sure you put something there so that you fix, like pin it, yeah. And this is the data set, test data set. I use 0.2, that is 20%. Now the next thing is, I remember from the PyCaret result, it shows, I said I selected 3 different algorithms. That is the random forest, ESRA3, and gradient regressor. So I started with random forest. I import a random forest regressor, and I use the data set I split it here. That is the input and the output. From the input and the output data set, I also use, I started with the training data set, that is the X train and the Y train. The X train, that is the input in the training data set. The Y train, that is the output in the training data set. That is what I use. This is just the model. Here, this is just the model. So I just fix the random state. Of course, there are other parameters that I can play around with, just to make sure I get the best result. So this is the model. I can run it. Yes, so this is it. Depending on the data set it takes and maybe the system properties, it may take longer or it may run faster, and maybe the input I provided. Now, I'm not sure of which parameters are in this model, so I print it here. These are all the parameter. You can change any of these. You can change them. So depending on what result you get, of course, maybe it may perform better or worse than the default setting. So it depends on you. Now, I've already trained my model here. There's the random forest regressor, and here I can now test it. Now, how do I test it? I asked it to predict. That is rfreg.predict, and I supplied with the X text. That is the input features in the test data set. That's what I used to make the prediction. That is after the training. Already it's familiar with the training data. It can now be used for the testing. Now, the testing, I asked it to predict, while this one I asked it to fit into this data. And in this case, I'm asking it to predict. Now, based on the result, based on the data set that I have, I am able to predict. However, you won't automatically see the result, but you know that this variable, what it stands for. So when you want to see the result, you just call on this, you just print this variable, you see your result. So I'm not interested in seeing the result for now, but what I'm interested in is to see the metrics is more important to me. So for the metrics, these are my metrics. For example, in the first case, I have Y test and Y predict. That is, I compare the target, the test target, the target in the test data set. Remember, we split it into 2. That is the training and the testing, and each of them has input and test output. That is the output is seen as target. So I compare the test, that is the Y test that it predicts, and the Y predicts. Sorry, the Y test, that is the original value that I have, and the original data that I have. and the Y predict, that is the Y, the data set, the settlement it predicts. Now, based on that, I said it should calculate the R score, that is the accuracy. And based on that, the accuracy it gives me is 0.96, which is approximately 96%. I remember the requirement for in engineering, that is the minimum is 95%. Of course, I've seen some papers that even have less than the 95%. So with this is something that is like reasonable, like yeah, technically is something that is reasonable. So I can present this result. I say, okay, this is what I got, and this is how I did it. And of course, the academia will accept it. So that is what I have for the R squared, that is the accuracy. And for the mean absolute error, this is what I have. For the mean square error, this is what I have. Now the aim is for me to maximize this and minimize these two. And also, I also compare the what's it called? The performance, because I can use the model to predict the same data set. For example, I've supplied it with the training data set and the test data set. Sorry, the training input and the training output. So I can decide to, okay, let me, in this case, in the case of the testing, keep my own training output and just supply it with the training input so that I can see what it will give me as the training output. I don't know if that is clear. I have my Y train and X train. Now I have used the Y train and the X train to train the model. So subsequently, I can decide to keep the Y train and use the X train and use the model to predict the X train. Of course, in that case, I'll expect the model to like perform best because it has already known my Y. So that is what I did here, and that's why here you can see the performance here on the trained data set is better. For example, the R squared, I have 99%, and the M, there is mean absolute error based on the training data set, I have 0.28. I have mean square error, which is 0.12. And if you compare it with this, you can see that the training is better. However, my testing is still meets the minimum requirement. So this is it for the random forest, and most of the other procedures is just the same thing, is repetition. So just that we have some differences when it comes to these parameters that I was talking about. So some of the models may have some different parameters that you may need to play around with, but basically it's just the same thing. So the next one is the extra tree regressor. I also import the extra tree regressor the same way I imported the random forest. Then I train it using the same what's it called, the same procedure. So if you can see here in the previous one, the only input I provide is the random state, which I said is just to make sure that you are getting the same scenario. You're using the same scenario like in all your in all cases. So in this case, instead of just fixing the random state, I also provide the number of estimators to be 100. So this one too, I print the parameters and see the default. So you can also play around with them. Now I train the model, fit, X train, Y train. And the next is to make prediction. Predict, X test, X train. X train is the output of the training data set. What else? X test is the output of the testing data set. So that is what I did. We can still run them. Sometimes. Okay, I didn't import it, sorry. Yes. So and I've done the prediction. So the next is to evaluate it using the matrix. This is something strange for everyone that knows. For example, it's strange for me to have 100% accuracy, and it's strange for me to have zero error. So that, to some extent, that is where we have concern about the overfitting and underfitting. I believe we may be familiar with those terms. Most of us will be. There is what we call overfitting and underfitting. Overfitting in the sense that the model can overland. For example, just capture exactly, when it captures exactly the training data set, it may perform worse when it comes to the testing. And but however, it should, as much as possible, try to be close to the training data set. So that is where we have those, the upper and the lower limit. There is overfitting and underfitting. So to some extent, I would say this model overfits this data, that is this extra 3, because it's giving me 100% accuracy and it's giving me 0% error, both the absolute and mean square error. So in that case, I'm expecting it to be, I'm expecting it, and I may not expect it to perform very well on the testing data set. And one of the ways to fix that is to increase the amount of data. When you increase the amount of data, you are minimizing the chances of overfitting. That is one of the method. And of course, my data set is just 420. So in some cases, you have thousands and thousands. So that is it basically. And the next thing is, I also try to print the result now. Okay, now I said, okay, let me print this result and make some comparisons. Now, for the result, this is what I have. I have the target, I have the prediction, I have the error. For example, when the target, in this case, when the target was 5, that is the actual settlement, if it's 5 millimeter. The model predict 5.15 millimeter. Now the error is minus 0.15. Remember, I said there is overestimation and underestimation. Please don't confuse that with overfitting and underfitting. They are two different things. Overestimation in such a way that, for example, maybe when the settlement is 5 millimeter, the model will predict, let's say, 10 millimeter. In that case, it overestimate. That may be safe in engineering practice, but then it is not economical. And I said earlier on that there should always be a balance between economy and safety. Of course, that is what engineers do. So there's this, when I do this, I can only see this when I check, that is when I print the result, the prediction result. Otherwise, I won't be able to see clearly how it performed. And also, even to even explore the result further, I even put some graphs. I'm not sure if I include them in the PPT. No, I didn't. Sorry. So when I print the result, this is what I'm able to see. For example, in this case, I have 15 millimeter settlement, and the model predict 13.73 millimeter. Now I have an error of about 1.27. Now I exported all this result and even make some further analysis so that I'll be able to communicate my result. Remember, I said there is need for one to communicate. There is communicating, proper good presentation of your result is as good as communicating and idea. And if you miss, like, poor presentation, if you poorly present your result, it will as well be like a miscommunication of a very good idea. So in order to be able to present my result very well, I just export it and analyze it in Excel, like plot them, make all the plots that I need, and that is that. So that is it. This is the target and this is the prediction. This is for another different model. This is for the extra 3. Yeah. Okay, this is for the test. This is for the test, and this is for the train, like the same training data. My time is running. So this is the last one, which is the gradient boost regressor. Also the same procedure. Import the model, train it, test it, maybe modify it if need be, and evaluate using the metrics. The basic, I just use these three metrics, which is the R squared, MAE, MSE. So there is it basically. I don't know if there is any other question. Any question, please?
Sorry, let me ask a question.
Okay, sir.
Who's going?
Can you hear me?
Yes.
Hello.
Yes, sir, it can be heard.
Okay. So my question is with actually fitting your model. So in a case whereby you fit your model, and so you have an instance whereby you have your result, like it presents you with an existence of multicollinearity, as you explained, with the correlation, checking the correlation of your data. So in a case where you have an instance of multicollinearity, so what method will you use to address this kind of issue?
For multicollinearity, sorry, let me just kind of briefly explain what multicollinearity is, for maybe for some of us that are not familiar with it. For example, in our data set, we have different features. We have minimum acceleration, we have maximum acceleration, we have minimum acceleration time, we have maximum acceleration time, we have speed and irregularity and settlement. That is from this table here. That is our data set. Now, there is a tendency that this data set that I have, there is a tendency that some of the features may be related, like strongly related to each other.
Yes.
I believe that is clear.
Yeah.
Now, in that case, there is possibility of this this strong correlation between two of the features to affect your result. And to avoid that, number one, you do that correlation check to make sure each of the features that you have in your data set is related to your what's it called, to your target. Secondly, there is a check for multicollinearity. I didn't do it here, but I did it in one other model like that, because I used the data set for different purposes. So I made sure that there is no strong multicollinearity between two of my features. So if you have how to access this is there are some packages to check the multicollinearity. And also you can also check if it happens that you notice the multicollinearity. The best thing I can suggest is to drop one of the features.
Okay, what about in a case whereby you have most of the data have this multicollinearity issue? Then and for example, let's say you have a sample of 20 variables, and then you have an existence of multicollinearity in this case, which most of the data are very are closely related, and they have strong correlation with the dependent variables. So now how can you determine the number of variables to drop or to remove from the sample size?
Okay. I'm trying to get this name. There's this regression, right? In regression, the minimum features you can use for regression is 2.
Yeah.
The minimum you can use is 2. So that means if, for example, 2 features gives you what you want, like the result you want, then that is fine. For example, as long as if, for example, I have settlement here as my target, if using just maximum acceleration can give me, let's say, 95, 96, 97% accuracy in predicting my settlement, then there's no point me including all the other features. What for?
Oh,
So as long as you're able to get what you need with as minimum features as possible, the goal is for you to predict it accurately.
yeah.
So there's no point putting like unnecessary features in the tags. I think you
Okay.
can drop as much as possible, provided like dropping them will improve your model accuracy.
So even though it is just one feature.
Even if it is just one feature, as long as that feature can give you like good prediction result,
Okay.
it's okay.
Okay. Thank you.
Welcome, sir. Is any other question? I have 15 minutes.
Yeah, hello, can you hear me?
Yes, I can hear you.
Yeah, it's regards with this where you like you reduce the dimension of the speed here, whereby you
Yes.
describe that you need to make the values to be around 1. So I
Yes.
want to ask, what if the values you reduce are like that particular magnitude, the higher magnitude, it's among the major features that determines the results. I don't know if after the learning, after the testing process, there is a way to refer back to that particular dimensions or magnitudes that you linearize to plus or minus 1. I don't know if you get my question.
Sorry, I didn't get you clearly. Can you please come
Like-
again?
Can you hear me?
Yes, I can hear you.
Yeah. So I said this, I think it's this speech. For example, now this speed now that you said is 350, 250, like varying. So you explained earlier that the magnitudes are higher than this minimum acceleration, maximum acceleration, whereby they are around or less than 1. So you explained that it's better to reduce it or categorize it to around that 1 or plus or minus 1. So I'm asking, is there any way whereby this, like maybe if you after the prediction, so there's a way to bring back the speed that we reduced, that we linearized?
Okay, I understand your question now. Thank you for
Yeah.
asking. If you remember, there was a time I was mentioning random state. Yes, yeah. Random state. For example,
Yeah.
if I didn't assign any value to this random state, the model is programmed in such a way that it operates based on probability. Now, probability will make it return like different result for the same situation, the same condition. For example, if I didn't pin this, if I rerun this, it will give me different result without changing anything. So the only thing that will help me is to pin it, number one. Now, going back to your question, if after making like the testing, the evaluation and everything, maybe it happens that I'm not okay with the result or I want to improve it. And one of the option I can apply is to go back to the features and standardize 1 or 2 of the features. If I happens to do that, I have to rerun all the code again. However, even if I didn't change it, if I didn't apply the random state, it will still not give me the same result. So advisably, assign a value to this random state, then go back to your That is from the beginning. Then go back to your features, standardize them and run them again. Otherwise, even if you change it here, it won't reflect in the result, in the model performance. You still have to run the code. I don't know if that answers your question.
Yeah. Thank you.
You're welcome.
Yeah. Also, sorry, with regards to this, when you choose input and output data from your data, like I missed the points you made there. Like, yeah, this
Okay.
place.
Okay. There are two different data splitting tasks. Number one is to split your data into test and training. Test in the sense that, okay, for the training, okay, sorry, let me come again. You split your data into input and output. You also split both the input and the output into test and training. I don't know if that is clear. You split the data into test and training, and you also split both the training and the testing into input and output.
Okay.
Yes. So it depends on you. You can do it whichever way you want. However, you have to make sure it's consistent. Consistent in such a way that, for example, because there's what we call index. Index like this. I don't know if you can see this. You have 0, 1, 2 to 335. Right? Now, these are values automatically assigned to the rows by the Python, by the program. Now, if for example, while splitting my data set, I happens to assign a test data set that is when I'm splitting, for example, I split it into input and output, right? Now for the input, I split my input into test and training. I have to make sure that the test data set corresponds, the test data set, so that is the input and the output in the test data set corresponds to each other. For example, if this 3.1 is a test data set, it will have an input and an output. Now I have to make sure that this output that is in the 3.3.1 corresponds to the input in that 3.3.1. Otherwise, it will result to an error. So in that case, to deal with that, I will advise that you first split it into training and testing. Although that was not what I did, but that would be more easier. Split it into training and testing. Now, for the training, you split it into output and input. Then also the testing, you split it into output and input. That would be less confusing. I don't know if that answers your question, or maybe you can ask again.
Thank you.
We have 7 more minutes. I don't know if there is any other question.
Yeah, it's like a question, but I don't know if it's a question. Maybe it's something you can maybe throw light on. It's interesting that when you mentioned the reason why you did not take acceleration data from the bridge and you instead took it from the train. I was thinking, I'm right, cool? Sorry.
Yes, sir. Yes, sir.
Okay, I was thinking that, okay, with all the primary, secondary, and even in some cases for high speed trains, in some cases you have like tertiary suspension systems. So I was wondering whether all these, or I was wondering how all these suspensions did not dump out this acceleration enough for the corresponding acceleration in the on the bridge to have more amplification, and then that also led me to, you know, towards the thought that I was now thinking about like in what position actually were the accelerometers installed, if you know this. I'm just
Okay.
curious.
Yeah, thank you very much for the, I can say, for making the highlight and also the question. Now, the background of the study is there is what we call vehicle scanning method. Vehicle scanning method in the sense that we can use a vehicle. Like initially it was like a model, just a model, a small model of vehicle that is used to extract bridge dynamic characteristics. For example, the mode shape and all those dynamic properties, the frequency and the rest of them. So that was the part of the background of the studies. And secondly, it was a study that confounds the fact that in a vehicle track bridge dynamic system, the most sensitive parameter to settlement is that train acceleration. So it's something that is confirmed in literatures. And for the position of the what's it called, of the accelerometer in the SIMPAC software, there is what we call reference coordinate, IREF, something like IREF, like the initial reference coordinate system. Like whatever you are doing, it's in reference to that coordinate. Now, there is also geometric center by default of each body. So in the previous studies, those studies about the vehicle scanning method, it is confirmed that the measurement obtained from the geometric center of that vehicle model gives more accurate result. So in this case, we use that marker on the center, geometric center of the train body. Of course, maybe in practice, it may be difficult to get that geometric center because maybe the place would be maybe hollow, like void, probably. But then we will try to get the position as close to that as possible in practice. But in the software, we're able to get that, and that is what we use. I don't know if
So
that answers
if
the
I
question.
understand, your data were all from like simulations?
Yes, sir. Yes, sir.
Oh, okay. So that one, my question was like, I wanted to know like how they would have how they would have I mean, I wanted to know where they would have installed the accelerometers on the train in, you know, in like vehicle experiment, in like real scenario, you know.
Yeah, I understand.
Yeah.
Like the
No, I was just it's just curiosity. I'm just
yeah, I
yeah.
get. It should be a position that is as close to the geometric center as possible.
Okay.
Yeah.
Thank you so much. Thank you.
You're welcome, sir. Thank you for asking.
Thank you so much, sir. Are there any other questions from the esteemed participants? Ezekiel, do you have any question?
No, no question for
All right,
today.
all right.
Thank you, bro. Yeah.
All right.
Thank you.
Yeah, I think there are no questions. So
All right.
do you mind rounding up?
All right. Thank you very much. So just to round up, there are different sources of data set, but the procedure is almost the same. It's always the same. Get your data, process your data, split the data, train the model, and evaluate it. Now, as I said, after processing the data, the next task is selecting the model. And that may be a bit complicated for most of us who are beginners, that is, who are not in the computer science discipline. So what helps for me in my own case, and I believe it will help most of us if it happens that we're going to do something similar, is the package called PyCaret. You can use it to, it will suggest models that will best fit into your data set. So use PyCaret to select your model, train the model, test the model and evaluate the model, and make sure you have a very good way of presenting your results. It matters a lot. And I think that is it basically. Thank you very much for the opportunity once again. I'm deeply honored. As I said earlier on, I know I'm not the best in this. So there are many other people who could do it better than me, but I'm honored.
I promise
Thank you so much for the
that
opportunity.
this presentation was wonderful. I promise
Thank you. Thank you so much for
telling
the
you, it
opportunity.
was great.
I'm
And
honored.
I'm sure other people who have participated in this kind of
Really, this presentation was very nice.
Yes, thank you.
Yeah.
We had a great time. Thank you, sir.
Thank you, Dr. MD Imran. You see, he has a PhD, and he has confirmed that your presentation is nice. Please, thank you so much. Thank you very much.
Thank you.
Thank you.
Thank
you. Really, it is nice.
Yeah. Yes.
We have got a lot of knowledge from this presentation.
Thank you so much.
Yeah. We want to appreciate the organizers and the presenter for a job well done. And you have taken some of us who are learners in the field of disaster management and safety to a greater level. So we hope that we can also learn from you outside this presentation, because it has really been too wonderful. And we thank you very much for an eloquent presentation. Thank you.
Thank you, sir.
Thank you very much. This is the end of our session today. Thank you very much. Thank you very much.
Thank you for conducting such a nice presentation.
Thank you so much.
Thank you, our organizer. We appreciate you so much.
Thank you.